Hello and welcome. Today, we delve into one of the most pivotal moments of the Pacific War. A chance encounter over the remote Alaskan marshes that would forever change the course of aerial combat. On July 10, 1942, American pilots spotted a seemingly invincible Japanese Zero, upside down and wrecked, lying hidden in treacherous terrain. An aircraft that would unveil deadly secrets about Japan's most legendary fighter. But what was truly extraordinary about this wreckage? Could a single damaged plane hold the key to turning the tide of a brutal war? How did this fragile, lightweight aircraft, built for speed and agility at all costs, become the ultimate Achilles heel? And what secrets did its battered remains reveal about Japanese engineering philosophy, secrets that would soon empower American pilots to outmaneuver and destroy their once mighty adversary? This discovery exposed a paradox. A fighter designed to be swift and nimble, sacrificing armor and safety, yet vulnerable to even minor damage and catastrophic failure under certain maneuvers. Could the very qualities that made it deadly in the sky, its speed, agility, and range, also be its undoing? How did studying this wreckage transform American tactics, allowing them to exploit its weaknesses and shift the balance of power? And what does this tell us about the broader strategic philosophies fueling the war? Values that prioritized offensive daring over pilot safety? In this video, we will trace the journey from that remote Alaskan crash site to the cutting-edge analysis that unlocked the Zero's hidden flaws. We will uncover how this single aircraft became a blueprint for American innovation, saving countless lives and turning the tide of the Pacific conflict. The story of the Akuden Zero is not just about a wrecked plane. It's about a revelation that forever altered aerial warfare. And now, the most exciting part begins. Let's go back to the moment when history's most pivotal secrets were finally uncovered, changing the face of war forever. On the morning of July 10 in the year 1942, the air was thick with tension over Akuten Island, a remote outpost in the vast Alaska Territory. High above the marshlands, a PBY Catalina seaplane sliced through the overcast sky, its observation windows providing a vital vantage point for those aboard. Within the confined space of the cockpit, machinist-mate Albert Knack cautiously pressed his binoculars against his eyes, his gaze fixed intently on the ground below, where a surprising and potentially game-changing sight unfolded. His hands trembled slightly as he focused on the landscape, aware that what lay beneath could alter the fate of the Pacific theater forever. Across the wings of the Catalina, unmistakable bright red circles adorned with Japan's rising sun emblem, symbols of their formidable Zero fighters, confirmed what every seasoned American pilot had been conditioned to believe. These aircraft were nearly invincible, an unstoppable force in the sky. Just beneath the plane, in the wet grass of the marsh, a Japanese Zero fighter was visible, upside down yet remarkably intact, suggesting that it had crash-landed or been forced to make a desperate landing. Meanwhile, in the cockpit of the patrol plane, Lieutenant William Thez had already begun piecing together his course. His aircraft had become lost temporarily within the dense fog banks that cloaked the Aleutian Islands, an often treacherous maze of weather and terrain. Using dead reckoning, a navigational technique relying on estimations of speed and direction, Thez had managed to reorient himself over the Shaiman Islands. After confirming his position, he plotted what seemed the best and most direct route back to Dutch Harbor, a critical U.S. military base. Surprisingly, this route took him right over Akuden Island, an unusual decision, as such a path was seldom flown, and it held the potential for critical discovery. What the Americans were witnessing that day could be a turning point in their understanding of the Pacific conflict. The route that Thez and Knack were on, though rarely traversed, was about to lead them to an object that would profoundly impact the course of the war. Neither of them could possibly realize the significance of the wreckage they had stumbled upon. If recovered, this aircraft would reveal an astonishing paradox in the design principles of wartime aircraft, a paradox that would be etched into history, not through technical manuals alone, but through lives saved in subsequent battles and strategic victories achieved in the years to come. The Japanese Zero had long been regarded by Allied forces as a nightmare, a machine built entirely on fear and respect. For nearly 7 months following the attack on Pearl Harbor, American pilots had faced this superior aircraft with trepidation. The Zero was fast, highly maneuverable, and boasted an unexpectedly long range, enabling it to dominate the skies across the vast expanses of the Pacific. Early battles over China against Soviet-built fighters had showcased the Zero's deadly efficiency, with kill ratios soaring as high as 12-1 in its favor. A Japanese strike force, including 36 Zeros, launched an attack in April of 1942, sinking British ships and shooting down 27 British aircraft at the cost of only 5 of their own fighters, an impressive testament to its prowess. The official response from American forces when confronting a Zero fighter was straightforward: if humiliating, retreat and avoid engagement. Dogfighting these aircraft, that is, engaging in close-range aerial combat, was regarded as a near-suicide mission. This was not out of cowardice but due to relentless, brutal mathematics of combat. American fighters that dared to turn and fight against the nimble Zeros often ended up crashing or being shot down. Their pilots' attempts at traditional tactics, such as turning to face the enemy head-on, rarely resulted in survival, as the Zero's superior speed and agility outmatched conventional fighting techniques. This deadly reality was exemplified on June 4, in the pivotal Battle of Midway, a mere 1,500 meters south of the sighting that Nak and Thez now studied. As part of Japan's larger strategy to seize the critical Midway Atoll, a diversionary force was dispatched to the Aleutian Islands to lure American attention away from the main assault. Among the Japanese personnel involved was a young, 19-year-old flight petty officer named Tadayoshi Koga, who had launched from the Japanese aircraft carrier Ryujo as part of the complex and daring plan. His mission, an elaborate piece of Japan's grand maneuver, was intended to draw American forces northward, away from the true target of their operation. In this context, the discovery of the wreckage on Akutan Island took on extraordinary significance, for it was more than just a damaged aircraft. It was a glimpse into a technological marvel that had defined aerial combat during the first years of the Pacific War. The entire strategic landscape and the understanding of Japan's air power would be forever altered if the aircraft could be recovered and studied. What the Americans were about to uncover would not only in the aftermath of the second strike on Dutch Harbor, Koga's aircraft, the distinguished Zero with the serial number 4593, found itself entangled in a desperate struggle for survival. This particular plane was part of a compact formation of 3 fighters dispatched to carry out a daring strafing run against the American naval base situated on a remote island within the Alaskan archipelago. Leading the attack, Koga and his 2 wingmen, Chief Petty Officer Makoto Endo and Petty Officer Sugo Shikarda, descended upon the harbor with lethal precision, wreaking havoc. With devastating effect, during their assault, they managed to shoot down a vital American PBY-5A Catalina flying boat and, in the chaos, strafed the survivors struggling in the icy waters below. However, amidst the chaos of the attack, harm came from an unexpected direction. Ground-based small arms fire found its mark on Koga's aircraft, striking with enough force to sever an important oil line. While the damage was not catastrophic at first, it set in motion a fatal chain of events. Within minutes, the aircraft's engine oil, now leaking copiously, mixed with the frigid Alaskan air, gradually depriving the engine of vital lubrication and leading to a rapid decline in performance. Approximately 25 miles east of Dutch Harbor, on Akutan Island, carefully designated by Japanese strategic planners as an emergency landing site, an underwater submarine of Japanese origin waited silently just offshore, prepared for a daring rescue mission should any pilots be forced to crash or ditch in the vicinity. As Koga's aircraft's oil pressure plummeted, he rapidly assessed his options, communicated his status to his wingman, and started maneuvering toward the safe haven of Akutan. From this distance, the island's grassy flat appeared seemingly perfect for landing. Located just half a mile inland from the broad, water-lined coast known as Broadbight, the field looked firm, inviting, and seemingly secure for landing under the circumstances. Yet, Shikarda, circling above in a vantage position, suddenly saw something alarming. The ground beneath the grass was not solid as it appeared but was, in fact, marshland, soft, treacherous, and perilous. Water shimmered visibly through the grass stalks, revealing the true nature of the terrain. He desperately tried to signal Koga to attempt a belly landing, an emergency maneuver designed for such compromised ground, hoping to spare the aircraft from catastrophic damage. Tragically, it was already too late. Koga, fully committed, had already lowered his landing gear and proceeded with what seemed like a standard landing approach. But as his Zero's wheels touched the grass, they sank almost instantly into the soggy, yielding mud beneath. The aircraft pitched forward with violent abruptness, flipping end over end in a dangerous tumble. When it finally came to a halt, it lay upside down, wings and fuselage mostly intact but vast sections mangled and broken. Inside the inverted cockpit, the tragic outcome was swift and devastating. Tadayoshi Koga, the pilot and a proud representative of Japan's Air Force, was instantly killed, his neck broken by the violent impact of the crash. Meanwhile, Endo and Shikarda remained circling above the wreckage, torn by their conflicting duties. Standard protocol in such dire circumstances demanded that any downed Zero in enemy territory be destroyed, to prevent the enemy from capturing valuable secrets and to neutralize potential intelligence. Yet, seeing Koga's battered but recognizable form entombed within the wreckage, the two wingmen hesitated, unwilling to harm their fallen comrade. For several agonizing hours, the duo circled the overturned aircraft, their fuel dwindling as menacing weather closed in around them. The decision weighed heavily on them. Should they comply with orders and destroy the aircraft, or attempt a rescue? Ultimately, they chose to retreat, turning westward toward their carrier, convinced that a Japanese submarine lurking nearby would soon arrive to recover Koga's body. Unbeknownst to them, the submarine searched diligently for hours but was hindered by an American destroyer, the USS Williamson, which actively patrolled the area and drove the submarine away. Thus, Koga's remains were left undisturbed in the marshy, remote spot, hidden from normal flight routes and unknown to the Americans. For a month, the wreck of the Zero remained concealed beneath the persistent veil of fog and rain, which cloaked the area in enduring secrecy and made detection exceedingly difficult. The terrain and weather obscured the aircraft from anyone flying overhead, rendering it essentially invisible from conventional aerial reconnaissance. Then, on a day marked by a break in the clouds, a glimmer of something unusual caught the eye of an American reconnaissance pilot. Lieutenant Knack, on a routine patrol, spotted what appeared to be a small aircraft through a faint opening in the thick cloud cover. Recognizing the importance of the find, On the 11th of July, Lieutenant Thieves led a landing party to investigate the site began their detailed examination of the Zero, carefully scrutinizing every inch of its battered frame, knowing that each discovery could hold vital clues about its origins and design. The first hours of their inspection proved as crucial as the test flights that had once defined this machine's reputation. They found that the aircraft was astonishingly lightweight, not only in its overall mass but also in every individual component. The outer shell of the plane felt startlingly thin beneath their fingers, almost fragile, like a shell that might crack under minimal pressure. When Scarborough tapped gently on the fuselage, he was met with a dull, hollow sound reminiscent of knocking on a tin can, an unsettling contrast to the formidable reputation of a fighter plane. His gaze then turned to the area around the cockpit, searching anxiously for familiar protective features. He examined the windshield, expecting to see the reinforced, armored glass typical of contemporary combat aircraft, but instead found standard, transparent panels that offered no additional protection. His inspection extended to the fuel tanks, which he expected to be reinforced with self-sealing capabilities designed to prevent catastrophic fires. However, he discovered only basic aluminum containers that lacked any self-sealing technology, simple, open-faced tanks with no rubber bladders or shock-absorbing features that were standard in American fighter aircraft. This absence of crucial defensive elements was glaring and deeply troubling. It stood in stark contradiction to everything American aeronautical engineers believed about the safety and survivability of fighter planes. Modern dogfighting aircraft, by then, were equipped with armor behind the pilot's seat, armored windshields, and self-sealing fuel tanks, features that, although increasing weight, dramatically enhanced wartime resilience and pilot safety. The Zero, however, had none of these protective measures, revealing a design philosophy that prioritized speed and maneuverability over defensive resilience. The recovery operation was fraught with challenges from the outset. The adverse weather conditions, famous in the region for sudden, violent storms and dense fog, made initial efforts to retrieve the aircraft extremely difficult. On July 12, Lieutenant Robert Kerms led a team that, in a solemn act, laid Koga to rest with a proper Christian burial in a designated nearby cemetery, an act of respect that transcended their wartime conflicts. The following days involved repeated attempts to recover the aircraft itself. The delivery ship, battling the unpredictable rough seas, lost its anchors several times, hampering progress. It wasn't until July 15 that the team finally succeeded in reaching the site with a barge. Preparation then began to carefully extract the Zero from its marshy resting place. They constructed a makeshift sledge to drag the aircraft across the muddy terrain toward the nearby beach. Astonishingly, even waterlogged and battered, the aircraft remained surprisingly light. 6 men working in unison found that they could maneuver the damaged fighter with relative ease, a testament to its slender design. Once secured, the Zero was transferred onto the USS Street Meal and transported across the vast expanse to Seattle, arriving on August 1. From there, it journeyed by barge along the coast to Naval Air Station North Island near San Diego, California. This entire process took almost a month, during which American intelligence officers meticulously examined photographs of the aircraft, debating every possible detail of its construction and capabilities. Upon arrival at North Island, the Zero was placed under constant guard by military police, not primarily to prevent sabotage, though that was a genuine concern, but to keep eager souvenir hunters at bay. Many mechanics, pilots, and engineers were eager to claim a fragment of the legendary fighter for themselves, driven by curiosity and admiration. Orders were clear. Anyone caught attempting unauthorized access or dismantling parts of the aircraft would face weapons. The guards maintained strict discipline, understanding the importance of preserving the aircraft as a valuable, tangible piece of wartime history. Meanwhile, the skilled Navy mechanics commenced a painstaking process of restoration and analysis. Their task was not merely to repair the physical damage but to understand the very essence of the Zero's design, its strengths, weaknesses, and the philosophy that had guided its creation. The meticulous work of experienced aircraft technicians was crucial in unraveling the secrets behind this legendary Japanese fighter, and every examination brought new insights into its singular build and operational philosophy. As they approached the enigmatic aircraft, their initial perceptions were tinged with cautious skepticism. Many had believed that the Zero was merely a crude imitation of Western fighters, built with subpar materials and assembled with noticeable sloppiness. This suspicion had been reinforced by propaganda, which painted the Japanese warplane as a clumsy replica incapable of matching the sophistication of its Allied counterparts. However, what they discovered upon closer inspection shattered these preconceived notions and left them genuinely astounded. The Zero was, in fact, a marvel of engineering ingenuity, meticulously crafted to achieve an extreme reduction in weight, making it an exceptionally agile and efficient fighter. Every element of the aircraft's design reflected an obsessive focus on minimizing mass without compromising strength or performance. The main wing spars, for instance, were constructed from a highly advanced material known as extra superduralumin, a lightweight, yet incredibly durable aluminum alloy developed by Sumitomo Metal Industries in the year 1936. This alloy was a unique blend of zinc and aluminum, which resulted in a material notably lighter and stronger than the standard aluminum typically used in aircraft manufacturing at that time, although it did possess a susceptibility to corrosion. The Japanese engineers addressed this vulnerability with a specialized zinc chromate coating applied after the fabrication process, representing a sophisticated approach to metallurgical challenges that rivaled, or perhaps even surpassed, contemporary American techniques. Inspection of the structural components revealed further ingenious measures taken to save weight. For example, the wing attachment fittings were minimized by permanently bonding the wings directly to the fuselage, thereby eliminating the need for bulky removable joints that would add unnecessary weight and complexity. Meanwhile, the aft section of the fuselage was designed to be detachable just behind the cockpit, simplifying maintenance procedures while ensuring that the forward fuselage remained as light as possible. The strategic placement of the engine near the leading edge of the wing allowed the designers to produce a shorter and lighter tail section, which improved overall balance and handling. Control surfaces, such as ailerons and elevators, were covered with fabric rather than the heavier metal used by American fighters, contributing further to weight savings. Even the landing gear struts were designed to be narrower than their American equivalents, reducing drag and weight without sacrificing structural integrity. The cockpit itself was a minimalist construct, providing the pilot with excellent visibility thanks to its streamlined framing. Yet it offered no protection or armor, highlighting a design philosophy focused squarely on weight reduction. During a recent crash investigation, a maintenance team found that they could straighten a bent vertical stabilizer, rudder, wing tips, flaps, and canopy with relative ease. The landing struts, which had been sheared off during the accident, required total replacement, yet overall repair efforts underscored that the aircraft's components were both well-engineered and resilient. The relic of the propeller, a three-blade unit crafted by Sumitomo, had been carefully inspected, cleaned, and reused. Despite sustaining some damage, it remained serviceable, serving as a testament to the quality and precision of Japanese manufacturing at the time. As the engineers measured and documented the aircraft's specifications, they determined that the fully loaded Zero weighed approximately 5,555 pounds. In comparative terms, the American Grumman F-4F Wildcat, which served as the primary carrier-based fighter for the United States Navy, had a weight of about 7,426 pounds. The Zero, therefore, was lighter by an astonishing 1,871 pounds, almost 2,000 pounds lighter, an incredible difference that would have significant implications for its performance. This weight advantage translated directly into superior performance metrics. The Zero's powertrain was a Nakajima Sake, a robust 14-cylinder radial engine capable of producing around 950 horsepower. Conversely, the Wildcat was powered by the Pratt & Whitney R1830 twin Wasp engine, which generated approximately 1,200 horsepower. Despite having 250 more horsepower, roughly a quarter more, the American fighter also carried 2,000 more pounds of weight. This meant that, in terms of power-to-weight ratio, the Zero possessed a decisive edge, allowing it to accelerate faster and climb more swiftly than its American adversary. Further evidence of the aircraft's remarkable efficiency came from examining its wing loading. The Zero carried about 24.3 pounds of weight per square foot of wing area, whereas the Wildcat's wing loading was approximately 28.6 pounds per square foot. The lower wing loading of the Zero meant it could execute tighter turns, climb at a faster rate, and maneuver with more agility and confidence, traits that made it a formidable opponent in dogfights. Physics, in this case, appeared to favor the Japanese fighter sharply, granting it an insurmountable advantage in scenarios demanding swift, nimble movements. However, as the mechanics delved deeper into the aircraft's fuel system, a troubling discovery emerged. Unlike the self-sealing tanks used by American aircraft, designed with multiple protective layers of rubber and other materials, the Japanese Zero employed simple aluminum fuel tanks. These tanks were thin-walled, and on September 20, in the year 1942, just 2 months following its recent crash, Lieutenant Commander Eddie Sanders climbed into the cockpit of the repaired Zero for what would be its inaugural test flight. Sanders, distinguished as one of the Navy's most seasoned and skilled test pilots, understood intimately that his life depended on precise assessment of the aircraft's true capabilities and inherent limitations. As he lowered himself into the cockpit, he couldn't help but notice how confined the interior felt compared to the spacious cockpits of American-made fighters. The Japanese engineering, regardless of its other qualities, was renowned for producing power plants that were remarkably reliable and consistent. After settling into the surprisingly lightweight seat, Sanders began the engine startup sequence, which proceeded smoothly, a testament to the engine's dependable design. Meticulously, he taxied the aircraft, mindful of the narrow track of the landing gear, which made ground handling somewhat more delicate and tricky. When he advanced the throttle, the Zero responded with an eagerness that was unexpectedly sharp, propelling it forward with a sense of brisk urgency. The takeoff roll was surprisingly short. In fact, the aircraft became airborne almost immediately, arching upward with an urgency that took Sanders by surprise. Once at a safe altitude, he initiated systemized testing to evaluate its handling and performance. Initially, he focused on fundamental flying characteristics: level flight, gentle turns, climbs, and descents. The control responses felt incredibly light, bordering on delicate, a sharp contrast to the more weighty controls of American fighters. Small movements on the stick elicited immediate and responsive maneuvering from the aircraft, which felt more akin to a nimble sports car than a cumbersome pickup truck. Having spent years piloting American fighters, Sanders appreciated the Zero's responsiveness but was also curious about its ultimate limits. He decided to push the aircraft's performance envelope further. In the process of testing its maximum speed, the Zero comfortably reached approximately 330 miles per hour, a speed that was indeed faster than the Wildcat fighters he was accustomed to, but not by a significant margin. Intrigued, Sanders then attempted a hard roll maneuver at cruise speed, expecting the ailerons, the control surfaces responsible for rolling the aircraft, to respond normally. Instead, he immediately encountered a startling stiffening of the ailerons, which suddenly lost their usual responsiveness. This unexpected stiffening of the control surfaces at higher speeds, at over 200 knots, signaled a potential aerodynamic or structural issue, one that required immediate attention and further investigation. The aircraft's design, optimized for agility and speed, seemed to have inherent vulnerabilities that became more pronounced under extreme conditions. Sanders' careful testing revealed both the strengths and the limitations of the Zero, painting a clearer picture of what this aircraft could do, and what dangers it might pose to its pilots under certain circumstances. As the testing progressed, Sanders observed that the Zero's rolling maneuvers seemed to lose speed and responsiveness, demanding an unnaturally high amount of force on the control stick. He conducted a series of tests, deliberately initiating rolls first to the left, then to the right. The aircraft responded with relative ease when rolling to the left. It was decisively less agile and more sluggish when turning to the right. This stark asymmetry would soon prove to be a vital piece of intelligence for American pilots in combat. In a dogfight scenario, a Zero pilot would likely develop a preference for executing left rolls, simply because they were more natural and controllable. Recognizing this tendency, an American pilot could leverage it to gain an advantage, setting the stage to steer the engagement into rightward rolls, where the Zero exhibited its sluggishness and lacked responsiveness. The next test was arguably more dangerous, riskier than any previous maneuver. Sanders positioned the Zero in a steep dive, then yanked hard on the control stick to induce negative acceleration, an effort to see how the aircraft would behave under such conditions. Suddenly, the engine coughed, sputtered, and then quit altogether. For a moment, all that could be heard was the relentless sound of wind rushing past the canopy. Sanders found himself flying just as a glider at 3,000 feet over the California coast, with no engine power and nothing left but his skill and composure. He maintained his calm, leveled the aircraft, and cunningly managed to restart the engine. Encouraged by this, Sanders repeated the test twice more, each time with identical results. The engine coughed, sputtered, and shut down. The key factor was revealed. The Zero's carburetor, a float-type design relying on gravity-fed fuel delivery, could not handle negative G-forces at all. When subjected to negative acceleration, fuel flow into the engine was interrupted entirely, causing it to stall. This discovery was exactly what American pilots needed to understand. When under attack by a Zero, they were advised not to attempt sharp turns or to fight its maneuvers directly. Instead, the better strategy was to push the stick forward aggressively, diving at high speeds while experiencing negative Gs. Because the American aircraft employed a pressure-type carburetor, it continued to operate normally under negative G conditions, unlike the Zero's engine. During those critical seconds of silence when the engine stalled, an American pilot had a window to increase distance or escape altogether, all without risking engine failure. Between September 20th and October 15th, Sanders completed no fewer than 24 test flights of this nature, each revealing new important insights. While the Zero's famed maneuverability was real, its ability to turn sharply at low speeds, under 200 miles per hour. Its capabilities diminished considerably at higher velocities. Once speeds exceeded 250 miles per hour, the Zero's responsiveness waned, and it became stiff, sluggish, and less agile. Conversely, American fighters, generally heavier but more powerful, gained a decisive advantage as speeds increased, able to outmaneuver the Zero in both speed and power. The comprehensive data from these tests was compiled into detailed technical reports and distributed to all fighter squadrons operating in the Pacific Theater. These reports, eagerly studied by pilots, confirmed what many had begun to suspect. The Zero, despite its legendary agility, had its limitations. It could be outclassed not by fighting exactly as the Japanese pilot preferred, but by imposing a different form of combat, one that exploited its flaws rather than its strengths. Long before the Akuden Zero was recovered, Commander John Thackweve had already developed his now famous maneuver, the Thackweve. He first employed it during the Battle of Midway on June 4, 1942, the same day the pilot Koga crashed his aircraft. Drawing on intelligence reports about the Zero's specific capabilities, Thackweve designed a defensive tactic involving two fighters flying side by side. When under attack, these fighters would execute a weaving motion toward each other, effectively drawing pursuers into a hook, where they could come into clearer view and be more easily engaged at close range. The captured Zero further validated Thackwev's theories, providing precise data on the aircraft's weaknesses. This intelligence, in turn, enabled the American pilots to refine their tactics further. They learned to fight the Zero using boom and zoom combat, taking advantage of altitude, speed, and vertical movement to their benefit. The strategy involved gaining an altitude advantage before diving at high speeds directly at the enemy, making a single, well-placed firing pass, then continuing the dive past the target to increase momentum. Following this, they would use superior speed to zoom back up to altitude and repeat the process, never allowing the aircraft to slow down or lose momentum. This approach emphasized speed, altitude, and swift, decisive attacks, exploiting the Zero's vulnerabilities at high speed and under negative G conditions. Harnessing the advantage of unmatched diving speed, robust structural integrity, and enhanced pilot protection, American forces discovered a strategic edge in their confrontation with the formidable Japanese Zero. When an enemy aircraft was captured intact, it became an invaluable asset, an object of intense scrutiny and testing. The captured Zero was subjected to a series of mock aerial combat exercises against the various types of American fighters, including F-4F Wildcats, P-38 Lightnings, and P-40 Warhawks. Every engagement was meticulously recorded on film, allowing pilots and engineers to study the Zero in action and glean insights into its operational strengths and vulnerabilities. Through these detailed analyses, pilots gained first-hand knowledge of how to capitalize on the aircraft's weaknesses. They observed, for example, that the Zero's ailerons would freeze at higher speeds, making precise maneuvering difficult and sluggish. Additionally, during negative G maneuvers, the Zero's engine often experienced cuts, causing temporary loss of power. The aircraft's heavier American counterparts, despite their superior firepower and armor, could also outdive the Zero, which was not built for sustained high-speed dives due to structural limitations. However, perhaps the most profound revelation was psychological rather than purely technical. Unlike the myth of the invincible warrior, the Zero proved to be vulnerable, an aircraft that, with the right tactics and knowledge, could be defeated. It was a marvel of engineering, designed flawlessly for specific mission profiles, particularly for agility and long-range strike capability, but it was not invincible. This understanding suddenly turned the tide of morale among American pilots, who had been initially overwhelmed and helpless faced with Japanese fighters. Equipped now with concrete tactical knowledge, they had a strategy. They learned how to fight smartly against the Zero, turning their disadvantages into advantages. Many of these lessons were reinforced by live combat simulations, dogfights that were recorded and carefully examined, where pilots identified fundamental weaknesses. They discovered that at speeds exceeding 200 knots, the Zero's ailerons would freeze, diminishing its agility and requiring more force to maneuver. The pilots realized they could exploit these shortcomings, and they did so eagerly. This critical intelligence rapidly spread across the fleet, transforming fighter training and preparation. New pilots, before ever engaging Zero in combat, learned to employ boom and zoom tactics, attacking quickly from a position of advantage and then climbing away to safety, taking advantage of the aircraft's structural weaknesses and limited diving capabilities. Veteran pilots shared their insights with a mixture of relief and vindication, recognizing that their sacrifices and early losses had not been in vain. Their painful experiences had laid the groundwork for strategic breakthroughs that now equipped them to face the enemy more confidently. Lieutenant Commander Eddie Sanders documented these findings comprehensively in an official report. He noted that the performance tests, similar to those conducted during Navy plane evaluations, immediately demonstrated the Zero's vulnerabilities. Specifically, the freezing of the ailerons at speeds above 200 knots meant that rolling maneuvers at those velocities necessitated significant effort on the controls, making rapid direction changes difficult. This knowledge was swiftly disseminated throughout the naval fleet, leading to widespread adaptation in tactics and training. In the years that followed, new pilots were trained to recognize and exploit these weaknesses even before encountering Zero fighters in combat. Veterans, feeling a renewed sense of purpose, shared crucial insights and strategies, an act of relief and a measure of vindication, affirming that the sacrifices made during earlier, less successful battles had not been meaningless. Instead, they had provided vital information that would ultimately save lives and turn the momentum of aerial combat. Lieutenant Colonel Kenneth Walsh, a Marine pilot credited with 21 confirmed kills and awarded the Medal of Honor, later expressed that understanding what to do when a Zero was on his tail had been instrumental in his survival. He credited the intelligence gleaned from the captured Zero, particularly the details about how to counter its maneuvers, with saving his life on multiple occasions. Walsh's tactical knowledge, obtained directly from studying the wreckage, had transformed many dangerous encounters into victories or survivable engagements. Similarly, fighter ace William Leonard, who would eventually retire as a rear admiral after tallying 6 confirmed victories, regarded the captured Zero as an extraordinary treasure trove of intelligence. To his knowledge, no other captured aircraft at that time had unveiled so many secrets simultaneously, secrets that were critically needed during an intense period of aerial warfare. In a broader context, Japanese military historian Masatake Okumiya, a lieutenant general in the Japan Air Self-Defense Force, acknowledged that the revelations uncovered from the Ikuden Zero dealt a blow to Japan's strategic prospects comparable to the devastating loss at Midway. The intelligence derived from this aircraft illuminated critical weaknesses that, once exploited, contributed to undermining Japanese morale and combat effectiveness. Beyond tactical insights, the influence of the Ikuden Zero extended deeply into aircraft design and development efforts. American engineers and designers studied the wreckage with unparalleled intensity, gleaning data to inform new aircraft construction. At the same time, The development of newer fighters like the in the wake of their intense combat experiences, military engineers and strategists drew critical lessons from the combat performance and characteristics of the Zero fighter. These lessons served as the foundation for developing and refining newer, more capable aircraft, such as the formidable Grumman F-6F Hellcat. This aircraft was designed to incorporate the most vital insights gained from studying the Zero, aiming to counter its strengths and exploit its vulnerabilities more effectively. One of the key advantages of the Hellcat was its remarkable speed, reaching a maximum of approximately 380 miles per hour, a feat that allowed it to outperform many of the Japanese fighters in terms of raw velocity. Moreover, it retained vital defensive features such as armor protection and self-sealing fuel tanks, which were crucial for survivability in the fierce battles over the Pacific. However, the Hellcat was specifically engineered to engage the Zero on terms more favorable to the American pilots, recognizing the Zero's predominant role in early Japanese air tactics and its notorious agility. The design of the Hellcat also incorporated crucial insights into the weaknesses that plagued the Zero. Primarily a high-speed fighter, the Zero struggled significantly during rapid, high-energy combat maneuvers when faced with an equally fast adversary. The Hellcat's powerful Pratt & Whitney R2800 double Wasp engine was a core element of this strategy. Producing around 2,000 horsepower, this engine delivered more than double the output of the Zero, enabling American pilots to effectively employ boom and zoom tactics, approaching rapidly, delivering a powerful attack, and then quickly retreating before retaliation. In November of the year 1943, the battered wreck of the Akuten Zero was paraded at Washington National Airport as a prized war trophy during celebrations marking the 25th anniversary of the U.S. Air Mail Service. Thousands of Americans flocked to see the aircraft that had become a symbol of Pacific region combat. The Zero's appearance was striking, sinister, predatory, and dangerous, embodying the enemy's fierce dedication and agility. Yet, few observers truly understood that what they saw was not just an aircraft but a representation of a radically different design philosophy compared to American fighters. As the war entered its next phase in 1944, the Zero was transferred back to North Island for use as a training aircraft. New American pilots, eager to understand their adversary, flew against this aircraft in a controlled environment, learning its capabilities and limitations firsthand. Additional Zero models, including a notable Model 520, captured during the liberation of Guam, joined the training fleet. These aircraft allowed pilots to familiarize themselves with the Zero's handling, weaknesses, and combat tactics before facing them in actual battles over the Philippines, Eniwetok, and Okinawa. The confrontations with the Akuten Zero in the skies of California marked an important chapter in the evolution of American pilot training and tactics. Through these engagements, pilots gained vital experience and confidence, which translated into a better strategic understanding of their opponent. As the war progressed, the contrast between American and Japanese aircraft design philosophies became increasingly stark. American engineers relentlessly improved fighter aircraft protection, emphasizing increased armor, self-sealing tanks, and greater overall durability. The introduction of the F-4U Corsair in 1943 exemplified this new approach. With its armor-plated structure, self-sealing fuel tanks, and an engine producing a staggering 2,000 horsepower, the Corsair was a powerhouse designed for survivability and firepower. Its immense power and robust construction made it a formidable opponent in dogfights and high-speed intercepts. Meanwhile, the P-38 Lightning showcased a different design philosophy, combining twin engines and extensive armament to ensure both firepower and pilot protection. Despite these advancements, Japanese aircraft designers responded by attempting to enhance the survivability of later Zero variants. For example, the A6M5, introduced in 1943, featured a 55mm armored glass windscreen and an 8mm armor plate placed behind the pilot's seat to offer additional protection. However, these modifications came at a cost. They increased the aircraft's weight by approximately 28%, while engine power grew only marginally, by about 16%, due to the Nakajima Sake engine's limitations, which remained close to 1,000 horsepower. Consequently, the later Zero models became slower, less maneuverable, and ultimately less effective than the earlier A6M2 variant flown by pilots like Koga. The Japanese engineers' efforts to retroactively include American-style protection in their aircraft failed because they lacked the powerful engines necessary to compensate for the added weight. Without the raw power to maintain agility and speed, these fighters sacrificed their primary advantage, their exceptional maneuverability. By the year 1944, American fighter pilots had established clear dominance over the skies of the Pacific. The great battles of that year vividly illustrated this shift, notably during the naval and air campaign known as the Marianas Turkey Shoot in June. During this decisive engagement, American fighters and ground-based anti-aircraft defenses managed to shoot down over 500 during the ongoing conflicts at sea. Many aviation accidents occurred during night carrier landings, often resulting from the challenging conditions and the pilot's limited experience. On the Japanese side, inexperienced pilots flying the iconic Mitsubishi Zero faced overwhelming odds when up against seasoned American aviators flying Hellcats and Corsairs. These veteran pilots had years of combat experience and a mastery of aerial warfare that their counterparts lacked, putting the Japanese pilots at a severe disadvantage. The attrition rate among Japanese pilots was devastatingly high, and the loss of experienced aviators became a critical problem for Japan. These seasoned pilots, some of whom had participated in the attack on Pearl Harbor and had previously dominated early campaigns across the Pacific, were systematically being killed in aircraft that no longer offered them sufficient protection. The rapid pace of the war, combined with the attrition of skilled pilots, meant Japan's training program could not keep up with the need to replace losses with equally qualified replacements. This created a widening gap in flying skill and combat effectiveness between experienced Japanese pilots and their less seasoned successors. The disparity was particularly evident as the war progressed into October of the year 1944 during the intense battle for the Philippines. At this stage, the Japanese began deploying Zero fighters in desperate kamikaze attacks, turning these aircraft into guided missiles designed to crash into American ships. When aircraft could no longer effectively serve in traditional dogfights, they were repurposed as suicide weapons, with the Zero becoming the primary craft used for these missions. The pilots of these aircraft, often lacking in combat experience, were ordered to sacrifice their aircraft deliberately by ramming enemy ships in a final, fatal attack.